Next, we have a talk with Dr. C. Shubha, Nirmala College for Women, Coimbatore. I kindly request Dr. Sindo, Assistant Professor of Department of Chemistry, to introduce the speaker.
Hello. Dear participants, it's my privilege to introduce today's speaker, Dr. C. Shubha, Nirmala College for Women, Coimbatore, India. Dr. Shubha is an accomplished academic with 18 years of teaching experience and active research, specializing in polymer chemistry and corrosion chemistry. Dr. Shubha's academic journey is rooted in excellence at every stage. She completed her PhD in chemistry from CBM College, Coimbatore. Her research focuses on the synthesis and application of novel polymeric materials as corrosion inhibitors. She has successfully completed funded projects and has supervised multiple PhD and MPhil scholars with 3 doctoral theses completed. Dr. Shubha's scholarly contributions include 21 research publications in peer-reviewed journals, 35 publications in conference proceedings, and 6 books with ISBN numbers. Dr. Shubha is also an active member of the broader scientific community. At the same time, she has built the professional ecosystem by organizing a wide range of academic events, from regional workshops and national seminars to international conferences and symposia. Beyond research and even leaderships, Dr. Shubha has made notable contributions to teaching innovations and academic quality assurance. Her expertise in governance, leadership, and management has led to several invited lectures on the revised NAC guidelines at multiple colleges, supporting institutions in strengthening their quality assurance processes. Dr. Shubha serves as editor for International Journal of Environmental Chemistry, the International Journal of Analytical and Applied Chemistry, and the International Journal of Green Chemistry, and as a reviewer for the International Journal of Creative Research Thoughts. She is also a life member of the International Association of Engineers, reflecting her engagement with the global engineering and scientific community. With this rich combinations of research excellence, academic leadership, editorial responsibility, and dedications to teaching, Dr. Shubha brings a deeply informed and practice-oriented perspective to our deliberations today. On behalf of the organizers, it's a great honor to welcome her as our speaker for this session.
Very good afternoon to everyone present here. I think it's your lunchtime, yes? So I'll try to complete my speech very fast. But I'm very happy to see that girl from Agriculture University was presenting. Yeah, very, very good. She was presenting very confidently, and she was facing so many questions from Sir. Very good. I appreciate you for that. Nowadays, students are not voluntarily coming for studying basic sciences. Yes, I think within 5 to 10 years, there will not be anyone to teach basic sciences, especially physics, chemistry, and mathematics. So I appreciate all of you, and mostly girls here. And it is very important for girls to be educated at this modern era to face the entire society. So I'm Shubha from Nirmala College for Women, Coimbatore, and my college is located at the heart of the city. And I invite you, every one of you, to our college also, so we can have a symposia or workshop or hands-on training like this. So I think you all know about polymer chemistry. Do you have a polymer chemistry paper in your syllabus? Yes. So we'll have an interacting session, and we'll complete it very fast. Okay. So since this international conferences talks about advances of science and technology, I'll tell you the advances or the emerging innovations in the polymer chemistry field, and I'll tell you what I'm doing in that research. So polymer is a branch of science, or you can say it is a part of organic chemistry. Now it stands at the heart of the modern science. How it stands at the heart of the modern science? Whatever field you take or you imagine, there is a material you have to give for the engineering side, or any field you think of, medical science field, electronics, engineering, and energy storage devices, sustainability. Wherever you go, there is a place for polymers to interact, because they, from basic plastic substances to high performance functionality polymers, they redefine the technological barriers. Or interdisciplinary research is what nowadays is encouraged between the different fields. So overview of my presentation, I'll give you some introduction about the polymer chemistry, and how the polymer sciences evolved from the ancient times till the modern era, and some of the fields, some few fields we'll see, the emerging innovations and the advanced applications, and I am what my research I am what doing with the polymers. So you look at the slide, you think of any substance or any materials, they play a major role in our daily life. by providing all the essential materials which makes us very comfort to live in this modern world. Yes, so we all know polymers are large molecules, and their versatile properties are making this material suitable for the wide range of applications. Okay, see, plastic containers are there. You think of our household, common household items, like plastic containers, packaging materials, water bottles, furnitures, everything is made up of synthetic polymers. You come to natural polymers. Can you say some example for natural polymers? Cellulose, huh, proteins, starch, everything you can give mention as examples for natural polymers. Okay, so they play or they influence our food materials, clothings, paper products, everything. They are coming from natural polymers. So you look at this. This, what is this? Can you tell me? That is a stunt. Yes, if you get a block in our heart, or stent is used, and polymeric or biodegradable polymers covers those stunt, and they'll keep the stunt where it is blocked. Okay, so after over a period of time, it dissolves inside itself. Okay, so there also we have the role of polymer. So what is a polymer? It is a low molecular weight organic compounds, carbon containing compounds. They are combined, forms a long chain, and many repeating units are combined together, and we are calling it as a polymer. Poly means we all know it is a many repeating units combined together. So you can extract the natural polymers from the plants and the animals. Synthetic polymers we can make in the laboratories. So this is and all, I think a short polymer chain can be called as oligomers, and many types of polymers are there. Random polymers, alternating copolymers, block copolymers, many things are there. So based on many basic principles, we can classify the polymers into different types. Only few I have mentioned here, but many types of polymers are available. Okay. So based on the natural, based on the principle of sources available, we can classify the polymers into natural, semi-synthetic, synthetic. We know what is a natural polymer. We know what is a synthetic polymer. So what is a semi-synthetic polymer? Derive the polymers from the natural resources and do some modifications chemically, and it is called a semi-synthetic polymer. Then based on the length or the nature of the monomer units, you can classify them into linear, branched, and cross-linked polymers. See here, you can call these as linear polymers. Yes, and this graft copolymer, it can be a branched polymer, and this is a cross-linked polymers. Sorry. So based on the mechanism or the polymerization reaction, they can be classified into addition polymerization and condensation polymerization. Addition is nothing but you take two monomers, combine it together, it is added as such. No molecule is removed or eliminated. It is an addition product. Condensation product, you take any two monomers, combine it. If you eliminate some molecules, like most probably it is water molecule, you will get a condensed product. So based on the nature of the monomer, it is classified into homopolymer and heteropolymer. If the monomers are same, like ethylene polymerizes with another ethylene, so you are getting polyethylene homopolymer. Heteropolymer if the two monomers are different. So based on the molecular force of attractions, it is classified into elastomers, fibers, thermo and thermosetting polymers. Okay, elastomers, their molecular force of attraction is very weak. Okay, like elastic, rubbery like substances. Fibers, they have a very high tensile strength, so their molecular force of attraction is high. Okay, so thermoplastics, they have a moderate molecular force of attraction. once they can be remolded. Okay, thermosetting plastics, once it is set, we cannot be remolded. So many polymerization techniques are there. Based on their reaction media, we can divide them into different types. So homogeneous bulk and solution, heterogeneous suspension, and emulsion polymerization. So bulk polymerization means it is a solvent-free process, one of the important process where the liquid monomer can be polymerized directly into a solid product. Okay, 100% polymerization is possible here, and our polymer will be pure also. We are adding a charge transfer reagent just to control the molecular weight of the polymer. Okay. So the next one is solution polymerization. Here our monomer can be combined with the initiator because to some agents, free radical reagents are needed to initiate the reaction. So initiator will be there, and this will be a that solvent what you are selecting should be an inert solvent. It should not react with our monomers or the initiators. Next is the suspension polymerization. Here the monomer which is insoluble in water, water insoluble monomers can be polymerized using this principle. That means monomer is suspended in water as a fine droplets. Okay, that bulk material will act as a polymerization nucleus. So 100% polymerization is possible here also. And what polymer you are getting here is, it will be like a spherical bead like structure or a pearl like structure. So this polymerization technique is otherwise called as pearl polymerization technique. So the next one is emulsion polymerization. Here our monomer, what it is mixed with surfactants, and it is dispersed in the reagent. Okay, and an interface is created between the water and the monomer. Okay, it will form a missile-like substance. I think you know it's in surfactants. It is a surface active reagent. So it forms a missile-like substance. So we can get a polymer using using stabilizing agents. So next, now we have seen the types of polymer, and we have prepared the polymers. Now we have to calculate the molecular weight of the polymer. So two different formulas are there. They are based on the number of molecules of the monomer along with the molecular weight. If you are able to know or calculate the degree of polymerization, using that technique also we can calculate the molecular weight. Experimentally, we can at lab, since we are all in arts and science college, our facility is very limited towards the research. So with the available facility, we can use viscometer to calculate the molecular weight, and spectral data, mass spectroscopy is nowadays used to calculate the molecular weight of the polymer. So coming to the history of polymer science, earlier days in pre-1900s, humans were making use of wood, wool, cotton, like naturally occurring polymers to make their living comfortable. Okay. So slowly they started modifying all those naturally occurring polymers, they started vulcanizing the rubber, and they started preparing celluloid compounds. Do you know what is in vulcanization of rubber? Sulfur. They have to treat it with the sulfur. They have started vulcanizing, and the first ever synthetic polymer was prepared by Leo Baekeland, and he prepared bakelite. I think you would have studied about the manufacture of bakelite. In 1907, he fully prepared this, and this is the first synthetic polymer prepared. And from there, the plastic age started. Okay, so from there, now we have an enormous functional polymers which find applications in many field. Uh, Starting here in 1920, only proposed that polymers are not only aggregates, they are the long chain compounds bonded together by covalent bonds. See, he only proposed it is a long chain and it is having a very high molecular weight. He was imagining, okay, about the molecular weight. This Hermann F. Mark, Hermann Francis Mark, he is considered as the father of polymer science. What he did was he was able to calculate the molecular weights of the polymer. Okay, so he was working with the XRD analytical tool, and he was proposing some theory based on the molecular forces of polymers, and he was able to calculate the molecular weight of the polymer, and he established a separate research institute for polymer science. Okay, so coming to the innovations, these only few fields I have given, but so many fields are there, you can Google it. Okay, so the first one is biodegradable polymers. This is one of the fastest growing research area, because we are using all types of plastics. And what we are doing after using those things? We are dumping in the environment. Okay, so it is creating a serious problem, environmental problem now. So the scientists are focused to prepare or dissolve this issue, and they are focusing their synthesis on the biodegradable polymer. Once it is prepared, or the fully biodegradable polymer, what now they are using is PLA and PHA. PLA is polylactic acid, PHA is hydroxyalkonates. Okay, so those are the biodegradable polymers nowadays they are using. Once it is prepared, if you are dumping in the environment also, if some microbiology activity happens on those polymers, they can be in the presence of air, aerobic degradation, or in the absence of air, they can be degraded into their biomass or carbon dioxide or methane gas, which is not much harmful to the environment. So recent researchers are focusing on this field. Benefits, if you look at the benefits of these biodegradable polymer, the biomedical field, now they have started synthesizing artificial organs like bones in the orthopedic fields, dental implants they are using. So in whatever field you go, you can see a role of biodegradable polymers in that field. So next is smart polymers, or you can call them as intelligent polymers. That means it is responsive to the environmental factors. If there is a temperature change, if there is a pH change, they can be, those materials can be used in sensors or any displays if you want to react with something. Now these polymers are used as a smart polymers. They are called as smart polymers. They are temperature responsive, electro responsive, photo, pH, ion, redox, glucose, and enzymatic responsive. All the factors, physically, chemically, biologically, they are responsive, and the focus, research focus is now mainly on synthesizing the smart polymers. So next is recyclable one. Earlier we had a linear economy model where we have synthesized everything, used it, and just we have disposed it. Okay, now what they are doing, they are designing the material so that we can reuse it or recycle it. Once we are using it, we have to reuse it, otherwise we have to recycle it. Okay. So next is the biomedical polymers or tissue engineering. Biomedical polymers, they finds a major application in the tissue engineering. That means they can act as a scaffolds. What do you mean by scaffolds? Scaffolds. It is there, right? Scaffolds. See, the anybody knows Tamil? No. See, this bridge work is all going on, right? When they start some building construction and all, they have a temporary platform where you can climb, right? climb and use. That is called a scaffolding. Okay, so these biopolymers, they mimic the what extracellular matrix. That means you can regenerate the skin or cartilage materials. For repairing the damaged tissues, they are now focusing on the biomedical polymers. Advanced polymer composites, you mix the polymeric materials with the fibers or nanocomposites, so you can have an advanced polymer composites. Nanotechnology, again, everybody knows what is a nanotechnology. I think yesterday you had a topic in that. So nanoscale preparation of polymers is now going on. Nanoscale means it is 100,000 smaller than our hair diameter of our hair armor. Okay, nanoscale means. So their surface area increases so that application studies can also be encouraged. Okay, green chemistry. So nowadays they are going into the green chemistry or applying green chemistry principle in the polymer chemistry synthesis so that we can avoid the environmental crisis. So advanced applications against whatever I've told you in the innovations. So this is a very interesting field, energy storage and energy conversion field, where the polymeric based devices plays a major role in the renewable energy resources. Okay, so that means in super capacitors, if you see, electrode and electrolyte materials are based on the polymers. Okay, polymeric membranes are used. Okay, how the energy is stored in super capacitors? Energy is accumulated in the form of charges between the electrode and the electrolyte. There will be an interface, and we can see the energy storage. So in those field also they are using polymers. Okay, so now we have seen all the fields, not all the fields, only few fields we have seen. What I am doing, or what my research work is with the polymer is oxidizole. We thought of preparing polyesters and polyamides by incorporating some heterocycles in the polymer backbone, and we have started preparing the polymer chain with the oxidizole. So I have given you the topic has the substituted oxidizole polymers. See, you can see the isomers of oxidizoles. I think you know what is heterocycle and heterocyclic chemistry, and it is a five-membered ring. Oxidizole is a five-membered ring. We have two nitrogens and one oxygen. These are the different isomers of oxidizoles, and we concentrated on this 1, 3, 4 oxidizole, where the second position and fifth position free. Okay, so we can substitute, or we can have a derived product of oxidizole, and if you want to pair the polyester or polyamides, you incorporate in some of the compound, prepare a monomer, then polymerize it. After synthesizing the polymer, you have to characterize it. Okay, so now first, if you are going into the research, polymeric research field, you just learn how polymers can be synthesized. Okay. So first decide, say whether we do some literature review, and from the literature review with the available facility, you can decide what kind of polymers or what application I'm going to do with the newly synthesized materials. Okay, according to it, you plan and synthesize. Okay, so if you want a polyester to be prepared, what is the polyester functional group? See, here you can see the linkage, polyester linkage. It is COO. Okay, so this is a monomer and this is a another monomer. So here, if you want the monomer, polyester COO linkage, I'm not comfortable with this. Okay, so we need one of the monomer to have a diol. Okay, dihydroxy property, dihydroxy functional group at the end. So if you combine it with the dicarboxylic acid, See here COOH, COOH. So we have taken an amino dicarboxylic acid. This is amino terephthalic acid. Okay. See if that is chemical what commercially available. Amino terephthalic acid is commercially available. This is the one we have synthesized. Sorry, we have synthesized in the laboratory. Okay, we have taken an oxidizole under some reaction condition. We have introduced the amino group this continuously for 2 to 3 hours, we were able to get this linkage. Okay, so this is one of the monomer we have taken. This is a dihydroxy, diol. It is a diol or dihydroxy groups present at both the ends. Okay, why we have selected this oxidizole? Look at this oxidizole. It is having 2 nitrogen atoms and 1 oxygen atoms, where the electrons are lone pair of electron or electronic sextet is more on that group. And when we looked at the literature survey, it has more number of biological applications based on the 134 oxidizole. So we have selected oxidizole and incorporated in our monomer. So next we have to have a dicarboxylic acid. So we have taken an amino dicarboxylic acid, and this is pyranaldehyde, and we combined both the things. Both are commercially available. Under some reaction conditions, we were able to link this pyranaldehyde with this amino terephthalic acid as a pendant ring. Okay, so here we have taken hydroxy, here we have taken furfural. So different modifications we have taken. Okay, this one is the other type of oxidizole, or we can say it is a symmetric oxidizole. In the second position and the fifth position, we are having the same thing. And if you want to prepare a polyamide, okay, sorry. See, if you want to synthesize a polyamide, we need this linkage, CONH. Okay, so CO can come from the dicarboxylic acid, and this NH linkage you can get it from the NH2 groups. Okay, so when you polycondense this, you will get a CONH linkage. So we were able to synthesize, we thought of synthesizing a symmetrical oxidizoles, and we were able to synthesize this compound also, and we made use of these available dicarboxylic acids. So this is the polyester synthesis. We have used a triphenyl phosphine and a very little amount of pyridine and NMP solvent heated at 140 degrees centigrade continuously for 6 to 8 hours, and we were able to synthesize the polymer. And this is the polyamide. We have prepared 6 different polymers. 4 are polyesters and 2 are polyamides. So now we have prepared everything. We have synthesized monomer. Then you have to confirm it. Okay, using the spectral studies, IR data and MR data, you confirm the functional groups present in the synthesized product, and synthesize your polymer, and you have to characterize the polymer. Okay, so you first we have tested the solubility with different different solvents, and we have done the spectral data analysis. Then we have checked the thermal stability of our polymer and the crystalline nature of our polymer. Okay, so in the monomer we had this diols and COOH group. Okay, so that this part of this hydroxy is missing here. So we got a very strong absorption peak for COO linkage. So we have checked with the thermal stabilities with the TGA. So I think you know what is a TGA. It measures the change in the weight when heated or cooled. Okay, so you can heat the compound with continuously for 10 degrees centigrade per minute or 20 degrees centigrade per minute, and you can see the thermal stability. See, this is the data we have observed for the polyesters and and for the polyamides, you look at this 10% weight loss. Okay, so polyester P1 starts degrading at 110 degrees centigrade. This is for the polyamides. It starts degrading at 130 degrees centigrade. So the first 10% weight loss, water particles or the moisture, suppose if it is present, or the occluded solvents, which if it is present, that can be eliminated at the first 10% weight loss. So when you compare this polyester value and polyamide value, polyamides are highly thermally stable than your esters. Okay, so next, we have done this XRD studies to know the crystalline shape of the polymer, crystalline, whether it is highly crystalline or whether it is an amorphous solid. We have done this crystallography studies, and it is a very good analytical tool where you can measure the size of the crystallic nature. Okay, so most of the polymer, they can have an amorphous structure, or they can have a crystalline structure. So you look at this data, and we were able to get P1 and P5 were able to get a high crystalline nature, and the others shows an amorphous nature. The crystallinity may be due to the presence of heteroatoms or those things present in the polymer backbone. Okay, so now we have synthesized the polymer, and now we have characterized it. Next thing, it should be useful to the society in some way or the other way. Okay, so we as I said earlier, we are in an arts and science or college, so we cannot, or I think there are some limitations to do a very higher end research. Okay, so we thought of the applications which can be done in our laboratory, in our college lab. So we have done the corrosion studies in our lab, and we took, or we have we applied these polymers as corrosion inhibitors. Okay, so I think you all know what is a corrosion. It is a very serious problem nowadays in the industries as well as in our houses. If we have any metallic structures at home without maintenance, what will happen? The structure gets destroyed, damaged. Okay, so to avoid that, in many industries, we thought of using giving these materials as corrosion inhibitors. Okay, so we have selected a material, aluminium. This is an aluminium sheet. We have selected an aluminium sheet. This is an mild steel. Here also you can do the analysis, but for this study we have selected aluminium sheets. Okay, so what are all the different methods you have to follow for the corrosion studies? Weight loss method, temperature studies, which you can do it in the lab. If you have a electrochemical workstation, you can do this impedance and polarization studies. Only this study you have to give it out. For SEM studies, it is called the SEM analysis, surface examination studies. Okay. So first, when after you have selected this metal, you have to go for elemental analysis of the metal sheets. Then this is the weight loss thing which you can do it in the lab. That is, you select a metal sheet, clean it with emery sheets, or clean it with acetone, and you prepare a test solution. We have done it in acid media. Many medias are there. You can select an alkaline media or saline media, any media you can select. But what we have done is we have selected an acid media, and we have immersed these metal sheets inside the solution. You can prepare a test solution blank with inhibitor or without inhibitor. Okay, without inhibitor means it acts as a blank material, blank solution. With inhibitor, it is a test solution. You immerse this cleaned, pre-weighed metal sheet inside the solution for an hour. Okay, you can select the time. You can do it for 1 hour study or 3 hour study. You can fix it. Okay. Keep it in to maintain a uniform temperature. You keep it in a water bath. So this is the thing, parameters, different parameters you are studying using this weight loss method. Average weight loss will be studying. That is pre-weighed metal sheets are kept inside the test solution. After an hour, you take it out, dry it and weigh it. So in the blank solution, you can see the major weight loss. In the test solution, it should be inhibited. So the weight loss should be decreased. Okay. So using these values, you can calculate the corrosion rate, degree of surface coverage, theta value, and the inhibition efficiency value. So as here you can see, as the inhibitor concentration increases, the inhibition efficiency also increases. Okay. So here I have shown you only the two different concentrations, but you can do in 4 or 5 different concentrations. Um, the weight loss method. Okay. So next is the same thing we have done the weight loss method, but at higher temperatures. Okay. So instead of room temperature also we have taken into account. But apart from room temperature, you can increase the temperature and do the same thing. What I have told you, do the same thing, but at the higher temperatures, you fix the concentration. Then you calculate the corrosion rate, surface coverage area, and inhibition efficiency. Here you look at the inhibition efficiency. As your temperature increases, this inhibition efficiency started decreasing. Okay, what does it mean? When you increase the temperature of the solution, when temperature is increased, the whatever molecules absorbed on the surface of the metal started dissolving. Dissorption. Abdina, what do you mean by dissorption? It is removed from the metal surface. Okay, so our inhibitors efficiency started decreasing. So this is for the polyamide. And based on the temperature studies, we were able to calculate the energy of activation, free energy of adsorption minus delta G adsorption values. And you can see here delta H value and delta S value. Okay. So I think energy of activation, you would have studied all those energy barrier diagram with reaction media you would have studied. Okay. So if the energy EA value is high, our energy barrier is high. So the reaction has to overcome that energy barrier. If if the value is high, you can say it is a very good the inhibitor molecule. Here delta G adsorption shows a negative value. This is a negative minus delta G adsorption. That means our inhibitor molecules, whatever adsorbed is physically adsorbed. There is no chemical reaction between the polymeric materials on the metal surface. Whatever inhibitor we are using, it is not reacting with the metal surface. Only physically it is adsorbed on the metal surface. Okay. So these you look at this delta H value. I think you know what is delta H is. What is delta H? Enthalpy, whether the reaction is exothermic or endothermic. So the values are positive. So the since the value is positive, it is an endothermic reaction. What do you mean by delta S? Entropy. Yes. So the negative values, more of the polymeric materials, they are showing negative values, and this shows the association mechanism. That is, whatever material is moving very freely, they get associated or on the metallic surface. Okay. So these are the things what I have told you. So we have done electrochemical polarization and electrochemical impedance study also. The first one is called the Tafel slope. Tafel slope. This is called Nyquist slope. Okay. So this Tafel slope, whatever curve is going upward, is this talks about the anodic current, and this is talking about the cathodic current. When we studied or when we looked at the data of all BA and BC values, they are not much. There is no much change. So BA value shows some change. So we have concluded that this inhibitor is of anodic type inhibitors. And this is Nyquist plot. If you look at the this is a semicircle. All the concentration showed a semicircle, perfect semicircle. So our corrosion is activation controlled corrosion. Okay. So these two are the Arrhenius plots. I think you know what is the Arrhenius equation. Yes. You would have studied. Yes. Can you tell me what is an Arrhenius equation? K is equal to A into minus EA by RT. So based on this plot, we are getting a straight line, and you have to calculate the slope and intercept of these lines in order to calculate these values, these EA values. Okay, so these EA values can be calculated using this graph. Okay, so coming to the mechanism of corrosion of aluminium in pure acid solutions, I think without, I told you, no, without inhibitor also we have to immerse our material. So what is this? Our medium is HCl. So okay, H plus Cl minus. The Cl minus, what it does, what it do is, we have an aluminium sheet. Okay, when it is immersed in a solution, the metal is dissoluted. That means it will become Al3 plus and 3 electrons is liberated. Okay, so in that position, what happens? This chlorine goes and attack on this aluminium surface, and corrosion starting taking place. So when you mix our material, what it happens? This is our polymer. This polymer, what does it do? It gets absorbed physically, or it covers the metal surface. How it covers? All the electronic cloud present in the over this polymer, they just cover the material so that this chlorine molecule cannot intervene in the absorption process. Here you can see all the electrons of the azole group, lone pairs of electron on oxygen, aromatic sextet, everything covers this metal surface, thereby our corrosion rate decreases. So these are the same images we have done for these without inhibitors, with inhibitors, and we were able to see the polymeric materials on the metal surface. So that's all about the corrosion inhibition studies. And whatever I'm going to tell you now is, I'm not going to detailing it. Just I'll tell you, these are the researches we have started now. We thought of preparing a metal complex with our polymeric material, and we have to apply it in the any application field. We have to select anyone, and as far of now, we have done with only the copper metal, and we were able to dissolve our this polymeric material in THF, and we were able to get some crystalline new material. Okay, so we have characterized, we have taken IR and UV only, and still we have to study the dipole moment and the geometrical structure of the polymer metal complex. Okay, so application, see, whatever you are doing in research, it should be useful to somebody. Okay, so if we prepare or if we succeed, we have to apply in any one of the field. Okay, so the next thing what we are doing with other student of mine, what is she doing? Sorry. We thought of synthesizing some new nitrogen containing organic compounds for applying all those organic compounds in the biomedical field for therapeutic applications. So next thing I told you, no, we were using oxidizole. Here we thought of using what is this? In the place of oxygen, nitrogen is there. Can you call what? Can you say what it is? It is a triazole compounds. Okay, second position is free, fifth position is free. So you can substitute and prepare this triazole compounds, and we are planning to study the docking stimulations of triazoles, and see whatever research work I told you is very small. In Tamil, we used to say, "Kattradu kaiyalavu, kalladadu ulagalavu." Okay. See, I can see students only, I think, see some 50, 60 students are here. All are busy in their mobile. Okay. So what I have told you, only some were listening. It's I can't say anything because it's a lunchtime, and I should not bore you. Okay, so that's why I went very fast. And whatever this research area is a very vast area. It's like a ocean. Okay, whatever we are doing, it's like one drop. In that one drop, what I have told you is just one small point. Okay, so very many opportunities are available in the research area. and they need only the basic science students. Okay, so I'm happy to see very many have students here, and I wish you all very best. You should come up in life and you should come to the R&D departments. Okay, so all the best. If you have any few questions, I can take. Thank you for your patient listening. See, this electrochemical field is very simple. This weight loss method and temperature method, you can do it in the lab. If you have project, you have to do a project at undergraduate level and postgraduate level, you can go for corrosion studies. Okay, it's very simple.
Ma'am, how much efficiency you got for the inhibitor you prepared, ma'am?
You can see the polyamides, they were showing a very high polyesters. Sorry, what happened? Polyamides were showing inhibition efficiency up to 96%, ma'am. And we have given to an industry in Coimbatore for industrial applications also. They were also very happy about that polymeric material. See here, this is a temperature studies. And this is the weight loss method. Here you can see the polymeric polyamides, they are showing up to 96% of efficiency. When you compare with the polymeric polyester, they were showing up to 86%. So we can give all those materials to for the industrial applications also.
So, ma'am, nitrogen containing compounds are more efficient. That's what.
If any heteroatoms are present, sulfur can also, yeah, you can do with the sulfur also. Thiosols,
Okay.
you can try. Because it is very easy to synthesize in the laboratory, and what many biological applications, when we went for literature survey, many biological applications were reported. So apart from biological applications, whether they can be applied here in this electrochemical field also, we thought of trying it, so we went for it. No, we have prepared the oxidizole. Only dicarboxylic, yeah, that is commercially available. Then hydroxybenzaldehyde also commercially available. Not simply mixing. There are 2-3 steps you have to follow. We have taken hydro, yeah, step by step. Step by step. Well, that can be done through microwaves, microwave ovens. We have tried once, but the yield is not like conventional method yield. So, yeah. But I tried once, but the yield is not good, so I avoided that.
Thank you, ma'am.
Thank you.
On behalf of the organizers and all participants, heartfelt thanks to our inspiring keynote speaker, Dr. C. Shubha. Your enlightening insights on polymer and corrosion chemistry, drawn from years of dedicated research and teaching, have truly enriched our international conference and sparked new ideas for sustainable progress. We are deeply grateful for your wisdom, warmth, and the passion you bring to mentoring young scholars and advancing green solutions. Your presence made this session memorable and uplifting. Thank you once again, Dr. Shubha ma'am, from bottom of our hearts. Thank you.
Now we will be having a photo session. After that, we will have lunch. Just 5 minutes, and then you can have chicken biryanis. Then veg biryani is also there. So you can ask for that. So by 2:45 you have to be here. So we'll start the valedictory function by 2:45. Okay. ഫോട്ടോസ് അവിടെയാണ് എടുക്കുന്നത് കേട്ടോ. അവിടെ ആ ഗ്രൗണ്ടിലെ സ്റ്റെപ്സ് കണ്ടില്ലേ? അപ്പം നമ്മുടെ കുട്ടികളൊന്ന് ഡയറക്റ്റ് ചെയ്യാം കുട്ടികളെ.
ആദർശ് കൂടെ പോകും ഇവിടെ ആന്റണി ചേട്ടൻ